Thank you everyone for coming here. Thank you everyone that is on the phone line. We welcome everyone to the September Policy Speaker Series from NASA's Carbon Research Program. Today, I would like to welcome Deborah Gordon. She is the Director of the Energy and Climate Program at the Carnegie Endowment for International Peace. And we also have Frances Rowland. She is a junior fellow at the Energy and Climate Program. They are going to be presenting, introducing the Oil Climate Index, better known as OCI, and applying NASA's satellite data to fill gaps in research decision making. The OCI is an open source assessment tool that is used to compare greenhouse gas emissions from oil and gas fields. She's going to be going into that to explain the OCI. The important thing here about the OCI it is that it is already in years, and there is opportunity to use more satellite data and CMS and carbon products in their analysis. And then the talk and the visit from Frances and from Deborah here, we are hoping that we can initiate a discussion about potential collaborations within the NASA carbon science community that can lead into using products in the future updates of OCI. So we'll have questions and discussion at the end of the presentation, but also feel free, I think, to stop Deborah for questions, and I leave you all with Deborah Gordon.
Thank you so much. I have to say I was thrilled that Adil reached out to me. You came upon it just by chance, I think, even though we had been working with Chris Elvidge at NOAA on the VIIR satellite data that we brought into this model. But it's a thrill to be here. If I could, I was telling Fran, if I could have written this script a long time ago to have connected to NASA at the beginning of the project, it would have even been better, but it's never too late, and I think that it would be fantastic to continue these conversations. So just a little bit about the Carnegie Endowment that all of you might not know. The Carnegie Endowment for International Peace is an NGO policy center, and we have research areas all over the world working with people from these regions in the world. And our mission is to advance peace through analysis and the development of fresh ideas, to engage directly with decision makers, with thought leaders, with businesses, and civil society at large. Most of Carnegie, I will say, is very regionally based. If I had to make an analog, I would say that Carnegie as a think tank NGO is a lot like the State Department. It's more diplomacy based. We have centers that are like, you have bureaus in the State Department. And so my energy and climate work is a little bit outstanding of what Carnegie does, because my background is chemical engineering and public policy and a scholar of those. And I'd started in the oil industry and worked for the Union of Concerned Scientists and taught at the Yale School of Forestry. I've kind of bridged a lot of different communities on energy and environmental issues, whereas I work with probably more political scientists and diplomats now at Carnegie. So just to give you a sense of why I'm doing this project in the first place, I started my career at Chevron, and this is back in the 80s, oil was oil. I mean, that's at least how oil had been discussed. And I would say since probably Rockefeller, oil was standard oil, and no one really thought much about it. And then fracking started happening, the Keystone Pipeline debate was raging already with oil sands, and this is what oil started to become, to my mind, which was from on your left, the lightest oil, which is now even lighter with condensates, which is more like cream soda. So you have that all the way down to the right where you're having, Athabasca oil sands that are basically semi-solid, or petcoke, a product that is solid. And when you start thinking about oil as a resource and realize that physically and chemically, it's not anything like one thing, that's what led me to ask the question, well, what does that mean for climate change? Right now, almost any analysis of climate change that builds in fossil fuels uses one number for oil's greenhouse gas emissions, 432 kilograms per barrel. And it turns out, as you'll see here in this work, we found that really the emissions probably range in life cycle from in the 300s to the 800 or 900s. So there's a huge range in life cycle greenhouse gas emissions for oil, depending on what kind of oil, how much gas, how the oil is managed, how it's produced, how it's refined, and what different slate of products. All oils don't. These things don't make the same products. They make very different things, and so you have to sum up all of that. So I ran back in 2013, I ran a big oil symposium at Carnegie, and on one of my panels was a professor at Stanford, Adam Brandt, and when this was all over, I approached him and I said, well, you have this assessment model for greenhouse gas emissions from production. And I know you work a lot on the low carbon fuel standard in California, which is, how dirty is gasoline from a climate perspective. But I want to turn this question on its head because of what I just showed you with the picture. I want to follow the barrel forward. I don't want to look at a couple of products that are important today that come out of the barrel. I want to know the whole life cycle emissions of each barrel of oil, not only to compare them, but to start to get smart about policy of how we manage different barrels differently, because we're going to need different management policies to do that. So I approached Adam. He said, this is a great idea. I would love to do it. And we brought in a colleague, Jules Burgesson, a professor at the University of Calgary, who was at that time just developing the first greenhouse gas assessment model for refining. And we pulled this together, and then we added to it, another colleague and I added to it an end-use model of all these different products. And so now we have a composite of these three, I'll show you here, these three models that comprise the Oil Climate Index. There's OPGI, Adam Brandt's model at Stanford, that's a production model, and it's just featured now. We just wrote an article in Science that just came out last week on this. There's Prelim, the refining model I told you at the University of Calgary from Jules Burgesson, and then this OPEM, which is an oil product emissions module that comes and takes all of the slates of products from different refined oils, and we put the greenhouse gas emissions to that. It's basically, these are engineering models, bottom up, process engineering models. It's basically conservation of matter. What goes in has to come out. We follow it through the processes. We get as much data as possible on these engineering processes that are happening to turn crude into oil and then get it transported around the world to be used. And there are some, I think we now have about 8 different petroleum products, and even that is much smaller than in reality because you get lots of different variations on the theme. It's not gasoline and diesel. It's a lot of stuff that comes out of the oil sector. The phases, we're going into phase 2.5, but I'll just give you a little backtrack on the phases. Phase 1 was 2015. This is when I approached Adam, Jules joined the program. We got enough data to model 30 global oils through the whole life cycle, production, refining, and end use. And it was about, our data set of these 30 oils was about 5% of global production, very varied. You could look at the archives online, but from every nation that produces oil on Earth was kind of represented in these 30s, and every type of oil. We were trying to get as much disparity as we possibly could find between these oils. And we found that there were large differences in the greenhouse gas emissions, about almost a factor of 2, 80% in total life cycle emissions. But in terms of comparing one oil to another in terms of its production or its refining, it was over a factor of 10. So there was a 10x difference between producing the emissions associated with producing the lowest emitting oil and the highest emitting oil, or refining the lowest emitting oil or refining the highest emitting oil. Those we decided were enough to push us on this project to figure out, well, let's make our N bigger and figure this out. So we went on to phase 2 and released in 2016, where we modeled 75 global oils, more strategically looking for even other places to find types of location and locations of oil, now covering about 30% of global oil production. And we confirmed our phase 1 results, which was these differences in terms of greenhouse gas emissions between global oils are large, and they're large enough to matter. And they matter for policy making and decision making. And now I can see here, they matter for data collection. What isn't the most important information that the world needs to know to manage the climate impacts of the global oil sector, which is huge and important in terms of climate change. But there are pointed things that we need to know to really manage this better. We don't need to know everything, but we need to know We need to know what we need to know, and we have a better sense of that now. We're currently working on phase 2.5, where it's a midterm reboot, which we're basically trying to dive now into methane. That was the next place that we were going to go. We felt because we had Jewel Burgesson and the University of Calgary in our partnership, we have a pretty good understanding of extra heavy oil. What we don't have is a good understanding of ultralight oil and condensate, and that's where methane becomes a really big problem in terms of your emissions profile. So what we're going to do is what we did with the VIIRS satellite. Before we had the VIIRS satellite data and before Chris Selvage came on to have that information, we started out in phase 1.0 to use country level estimates that the World Bank had. And then we found out about VIIRS, and then in phase 2, we incorporated the satellite data. We're going to do that now with 2.5. We're going to incorporate the International Energy Agency's country-level data for methane, and then hope to get from NASA satellite data in OCI phase 3.0 for next year to build in actual ground, a better sense of what actually is happening from satellite measurements that we can then attribute to the ground to understand where the methane is coming from. So this is just the VIIRS satellite data on our oil climate index map. We need to update it. This is 2014 from phase 2. We need to still find out what the most recent data is as we go into this next phase. But here you can see basically the VIIRS satellite total emissions from annual flaring at different amounts of gas that are released. Red is more gas being released. And all the bubbles on here that I'll show you in a second on the web tool, all of the bubbles on here are our 75 global oil fields. The size of the bubble is the total emissions. Yeah?
Is this carbon or is it CO2 or does it include methane? What's included?
It's greenhouse gas equivalent, and at this point it is CO2, the best methane assessment that we could get in OCI phase 2.0, which I will say is probably undercounting a lot, and N2O.
And N2O, so those circles include N2O.
And because we could do that because we know the equipment that's processing this oil through the whole supply chain, we know we have a relatively good handle on the process. We have a very good handle on the process and a relatively good handle on that equipment, and there are emission factors associated.
But you looked at them separately because the carbon, the greenhouse gases behave one way and the nitrogen compounds are different in terms of their environment.
Right now they're put in as a global warming potential to just add to the total, but we can split them out. So, as I said, we have used now up to this date the CMS data for flaring through 2014, and our interests for the near future are to update as soon as possible the VIIRS satellite data to we don't know what year, maybe whatever the most recent data will be when we launch 2.5, 2018, 2017 data. Identifying and incorporating the methane data, which is what I was saying our next big focus is, and then using real-time satellite data in the OCI ultimately would be fantastic. As much as possible, as there is information feed from what's being picked up by satellites, we can bring some of that information into the Oil Climate Index. And in the long term, and it goes to your question a little bit, in the long term, we have underlying these data in the model that we haven't used air pollutants, and we also have land use estimates. And so to the extent that we might be able to build in satellite data for land use and air pollution and have those analytics be another frame of the OCI, I think would be a really important thing. Land use, of course, of development and management of these facilities that are all over the world. But air pollution, because, and it's more my background, that I think that there are a lot of pushes and pulls between air pollution and climate change, and you have to think about both of them. As you were saying, it's very hard to necessarily know that you'll fix one and you might, harm another. I think of the diesel scandal in Germany as I say that. So here I was going to very quickly give you a sense, and we think that people online can see this? Yeah. So I was just going to show you, because you can all, it's an open source model. I have, Fran, here we can hand, this has the URL on it, so you can play with it later. And I was just going to give you a sense of what is on OCI 2.0. So let's go to the map that you were just looking at. And the first thing I'm going to do is just zoom in to a field here. So I'm zooming into Eagleford in Texas. And what you'll see is we ultimately have oil field boundaries that underlay where the flaring emissions are. So what we can do is we can start to attribute or have a guidepost for where the emissions might be coming from, especially when you get to something like methane. These are flares, so you can see them. But when you get to methane, you need as much help as you can get to manage it, because you can't really see it that easily in real time unless you have LiDAR or other equipment right on you. So ultimately, what we'd love to do is have the methane data also on this page as a heat map, and with, as a different screen with the flaring data, and then you can start to see where the methane emissions are being picked up in relationship to where these oil fields are around the world. And then I was going to show you, it's a much larger site, but I wanted to just give you like 4 different plays with it. So here's where we stack up the different total greenhouse gas emissions is the full bar, and then you could see shades going back to whether the darkest is upstream production and the lightest in the middle is refining, of how these oils end up stacking up. And if you look at just the industry's responsibility, you'll see that the emissions totally change around in terms of priority order. So this would be ranking the greenhouse gas emissions based on the production emissions and the refining emissions. These would be emissions that industry can control, as opposed to the total emissions, which also incorporate the use of fossil fuels, of petroleum products, which is jet fuel and trucks and petrochemical feedstock and everything. So that's just, you get a whole different set when you change a priority of what's the responsibility. And then if I wanted to look here and say, well, what if I really was only concerned about North American oils? I really want to have a sense of how those stack up against one another. And as you hover over these bars, you end up seeing where in the supply chain the emissions occur. So how they add up. And by knowing where they occur, you, like I said before, you get much smarter about what you're managing. This is a really difficult sector. This is why we probably globally went to coal first and not to oil. This is a very difficult sector because it's big and it's complex, and if you deal with it monolithically, you can't get anywhere. It's almost too big to manage or to go for. But when you start to understand this, we're having oil companies come to us and ask for our help on how to manage their emissions, because they don't really profit by managing their emissions. They're required to manage their emissions, but they know what they know. But when you start to get smart about it from an emissions point of view, you kind of identify different opportunities. So then I was going to just show you here, I wanted to give you a sense of how this goes. So, oops. So here's Eagleford condensate. We were seeing that on the map before. And Eagleford condensate, its emissions split out this way. So if it's total 574 estimated kilograms per barrel, it splits out with upstream emissions being relatively large, actually, if you look at downstream. And then refining it, pretty easy. It's very light, easy oil. And then downstream, these are the sum of the products. These are all emission values in the column. But I wanted to show you what happens when I compare this to, let me compare this to Brazil Frade. Oops. So Brazil Frade has almost identical total greenhouse gas emissions in a barrel of it. So if you had a barrel of Eagleford and a barrel of Brazil Frade, they would almost be, from a total life cycle perspective, the same emissions footprint. But if you look at where their emissions are, they're actually kind of diametrically opposed. So Brazil Frade has its emissions not in terms of its production, but much more in terms of its refining and end use. So you end up with a whole different strategy for this barrel of oil than you would need to reduce the emissions from another barrel of oil, which becomes a very important part of the conversation when you're trying to do successful policy making. And then last but not least, I will show you on the analysis page. So this is basically just all of the oils. You can sort them by different things, but the y-axis here is total greenhouse gas emissions we were just looking at. The colors are the types of oil they are. And then they happen to be arranged by gravity. One of the interesting things I'll say before I show you what I was going to do is that my first going in on this was, I remember this conversation very clearly with Adam Brandt at Stanford, and I said, I was looking at the carbon contained in global oils, and I said, can't we just basically know their gravity? Because everyone collects gravity of oil. That's how, if you wanted to know an oil's characteristic, you could find out open source anywhere what its specific gravity is, its API gravity. I said, can't we just use gravity as a metric? And he said, it will not be that easy. And then when we got to this part of the project and I saw the graph, and it's like, you're right, we can't use gravity as an estimate for greenhouse gas emissions, which is a real problem because for the last 100 years we've been collecting that data. So that is great data that we have. It's just not a good link to climate change, which is a problem. So here, I'll just give you a sense. So far, some of the policy solutions that we've played with that we noticed right away as we analyze this more in terms of innovations that could happen in the sector to reduce its greenhouse gas emissions if we started targeting different oils based on where their emissions are, were these things. One is that a lot of depleted oils, California, Indonesia, use a tremendous amount of steam to get them out of the ground, and they use natural gas to generate that steam. So there are already projects, oops, I clicked the other way. So if you notice here, I should tell you, look, I'll go back to nose solar steam. So start looking at the bubbles going down, and different bubbles will start going down. So if I'm gonna use 50% of my solar steam, and I'm gonna generate my steam using concentrated solar, which they do in California and in 1 or 2 oil fields in Oman, then I start to bend the curve there. If I'm going to reduce my flaring, I start reducing emissions there. A lot of the world's oil is very watery. Some oils you have to pull up about 100 barrels of water for every 1 barrel of oil. You can manage that water. The Permian's starting to think about this very seriously in Texas. You can manage it totally differently. You can bend it there. And then from the heaviest oils in the world, if you don't burn the pet coke, and Suncor now, because of our work, is actually sequestering half of their pet coke to reclaim mines and reclaim pits. Instead of selling this stuff to China that's dirtier than coal, they're actually using it as activated carbon almost, or like a filler. And they're putting liners in and they're not burning it. They're using it for another sequestered use. So what you start to do is if you're really strategic about this sector, you can start to pick off the problems in these oils and change the whole way that the sector works and what its emissions are, but you haven't made some sort of grand pronouncement to get off oil, which is the hard thing to do. It's going to be much easier to change the oil sector and get smart about doing this than it is for all of us not to use oil in the first place. So that was can we go back a deal to so that's the oil climate index, just a few things. In phase 3, what we want to do is renewable hydrogen. A lot of hydrogen goes into the refining sector to turn especially carbon-rich into product. That hydrogen right now comes from steam reforming methane. It's one of the single dirtiest things we do in the energy sector. And we probably, because it's steam reforming methane, we're probably leaking a lot of methane along the way that we're not even aware of. So you have that additional emission. And so what we're trying to push, and I'd love to see Canada do this, and we're talking to them about it, is actually using renewable sources of hydrogen. So using the capital of the oil sector to start thinking about a renewable sector, which would be renewable hydrogen, which is in part of the Shell Sky scenario. Shell Oil just was talking about this. And you have some operational ways that the industry can actually invest to start moving this forward to a different place by taking away some of the dirtiest stuff that they do. So now in terms of you guys, like what we've been able to find. I mean, it was Fran's predecessor, Smriti Kimbley, and I started this on the methane data collection. We have a junior fellow rotation. Fran just started, came to us from the University of North Carolina, and so she picked up the ball. And now we're starting to look at this again. And you'll see here where we hit some dead ends and roadblocks, and we don't really know where to go with the methane data like we've done with VEERS, but bringing methane satellite data into the oil climate index. But our aim is to obtain the methane data so that we can put it on an overlay of what is now 75 global oil fields and where we're building in 40% of global gas fields. So we're gonna have about 50% of global gas production in OCI 3.0 in here as well. So we'll have oil and gas, and we'd love to have methane. So this would be my, you're going to laugh when I say gold plates. This is all I know. You're going to see how ignorant I am when I say this. But I was transfixed by Siamachi. When Siamachi found the hot spot in the Four Corners of New Mexico, I got really excited because I started thinking, wow, we could do this. Like, we could actually take satellite data and find problems that are out there. It turns out it's in the San Juan Basin. So we knew what oil field, and they eventually found the problem. We knew which oil field this was coming from because we had a satellite that identified a hot spot, and then we could overlay and see, where the problem was. So in the near future, our interest is to have global spatial coverage because, as you saw on the map, we have global oils and gas fields. It can't just be in one geography. I mean, we can have it in one geography, but it would be unfair in a strange way only to zero in on one geography. It would be ideal to have global coverage, to have the most recent temporal coverage available, ultimately to capture real-time data. But honestly, at this point, like the satellite data for VIIRS, I'm almost happy to take any year's data. I would prefer it to be 2012 or later because I think that the oil sector with fracking really changed around 2012. And so if you had data that was much older than that, say 2000, it wouldn't capture what the oil industry is doing right now. And to have measurements from an appropriate altitude, either surface or near surface level. One of the problems you'll see in a second that we ran into, I think it was with AIRS, was that it was at a different pressure gradient and too high up, and so it wasn't going to show us exactly what we needed to do like Siamachi did. That was more about how the emissions are on the ground or close to the ground. And then ideally having data that is visually workable, whether that's, I don't know enough of your business to know whether it's L3 level data or L2 level data, but just something that represents itself in a way like the VIIRS satellite data does that can make, that an observer, a non-expert observer can make sense of what they're seeing. In terms of the roadblocks we've had to date from NASA data, on the AIRS Aqua data, last year, Smriti and I went through this whole exercise where we got the AIRS data for 2016 and we created this raster. It now lives at the World Bank, actually. They ended up uploading all of this into their files. But we ended up, it was at too high of a level. What was it? 400 HPA, and so we ended up not having any ground truth to what was going on. So this is where it must have transported eventually, but it wasn't going to help us in terms of those oil field boundaries. And so somehow translating this on, to about 1,000 HPA would be much more useful for what we're trying to do. So Giovanni shows methane at 1,000 HPA, but we've been told that, or I think this happened with Smriti, she was told that observations at this level are sparse and maybe not so reliable. I don't know, but it might be something that's at least at a level that would be helpful for us. It's a matter of whether the data is up to it, and whether the AIRS satellite data has improved sensitivity at 1,000 HPA or not. That these are questions more for you that I, would love to get answers to, and not even answers to questions. The goal in mind is really to get methane observations that we can have in the Oil Climate Index, and it might not come from AIRS. Maybe that isn't the right tool to do it, but these are just the avenues we've been down trying to do it. And are the models that convert high altitude measurements that estimate near service, the GEOS-Chem that happens out of Harvard, are those tools, because we saw what we could get at 400 HPA, like are those tools good enough to bring us to a level, a modeled level that is closer to ground? We also looked at TES on Aura, and we weren't really clear how, we can find 2012 data, but there's a toggle for up to 2016, but when you go on 2016, there's nothing there for 2014, 15, 16. It's like it's there, but when you go there, it says no data found. So we weren't sure if that might be an opportunity. And would data from 680 or so HPA be relevant to ground level? Like, is that the right satellite data to use in the first place or not, was a question. And then in terms of other institutions' products that we've been talking a lot about, and I know that you work with a lot of others' instruments and collaborate as well, just to give you a sense, on Transo on GOSAT, the Japanese satellite, it was, as we understood it, only at this 400 HPA and not, like AIRS is, not really useful for us. For POMI, we're excited about, but we don't know that much about it. It's going to release its first data in October, I believe. And we don't know if the data will be OCI ready or not, but would love to see if you have any sense. Is it L2 level? Is the resolution right? Is it L2? Is it L3? How will it be visualized? EDGAR we looked at, there was some information that Adil sent us that that there's a lot of satellite work with EDGAR. But the best that we can understand from EDGAR is that it's basically a bottom-up calculation of emissions activity. So it's doing it a less better way, but much broader and inclusive way than what we're doing. So it's all activity globally or wherever they can get their data for sectors well beyond oil. And what we're doing for oil is more specific than what they've done for oil. They're just collecting basic, reported emissions out of greenhouse gas inventories, and we're actually doing life cycle assessments that mass balance in and out, like the whole thing on these oil fields. So we don't think that EDGAR is useful unless you have any other information. There's the new methane satellite that's going up by EDF, so I don't know, I have contacts at EDF, but I don't know how much you'll work with them, but it's in a 2021 launch, so it's certainly not really anything that's useful for us in the OCI anytime soon. And then the last thing I want to throw out there, because I've had conversations with folks at Brown. I also am a senior fellow at Brown University, so I have contacts there. And someone recently asked me, what about these methane craters in Siberia and any other methane venting pingos that might be in Alaska or elsewhere in the world? And there's some theories out there that they might actually be caused by oil and gas extraction. So we are interested in them, not just because they're sources of methane and they'll be relevant in terms of how large they are compared to the work that we're finding from oil itself, but also because they might be caused by oil and gas drilling and production. And I didn't know if anyone at NASA was analyzing or mapping that in terms of the methane emissions from these craters that are opening up in Siberia. And then this is the last slide. I'll just leave. It's a bit of a repeat from the slide before, but I made more details here. So this is just like potential OCI inputs that we think might be able to come from CMS data. In the near term, just reviewing, updating the VIIR satellite data, which I think will be relatively easy to do. And I could certainly talk to Chris Elvidge, who I know well. But anyone here that works on that, I'd love to talk to. Identifying and incorporating the global methane data that I've been talking mostly about. That's a little bit in the realm of how CMACHI had been done but improved upon from everything you're doing. And then in the long term, trying to see if we could break out black carbon, which is going to be a really big part of the oil and gas sector and is not yet really being captured, has not yet captured the imagination of climate change policymakers in terms of inorganic black carbon especially. I'm interested in ethane as well as methane because ethane not only is growing in concentrations in the atmosphere, but because ethane has much fewer sources. In fact, it's almost always oil and gas. And because we are fracking and producing unusually high levels of gas, we're going to be repegging probably our petrochemical industry here, which has already started. And so ethane is going to only be a pollutant that becomes more and more important. And ethane is both ozone, but it's also a short-term climate forcer. And it's less so than methane, but still there. And it also, when co-located with methane, can be an indication of that is a source from the oil and gas sector. So I'm interested in that. The other criteria, pollutants, maybe land use disruption. There's certainly fields that we have around the world that are in rainforests and that are also in peat bogs and other places where we just have a very crude 0-1 ranking of whether they're rich carbon land use or not. It's like a high, medium, low. And what we don't have right now is anything other than that. We have very basic default for land use disruption in here. It's there, ready to be explored, but it's not been. And then any other opportunities that you all see, having heard this, that you think that there's something being measured or to be measured that could really be relevant. I'd love to continue any and all conversations. So with that,
Thank you.
Yeah.
Questions?
So, you don't have to measure everything with the satellite. Because a lot of things, especially from specific natural sources, are co-emitted with similar proportions. So you might be able to get the lead emissions or nitrogen compounds or something because they're co-emitted in a certain ratio with what we can measure from space. Now, it does require making those in situ measurements in more detail. But especially for the trace species, that seems like the right way to go, I would think.
Yeah, and it is something we could do because we have we have the flow chart in these of what equipment are in place. And so to the extent that we know if something is co-emitted and a certain ratio that feels like it seems like it's relatively stable, then we could have that in there. So any guidance you have on that, I'd love to get on exactly which of the trace gases it makes the most sense to do that with.
So a question about, has similar exercise been done for coal? Or is it only oil?
Only oil, and when we finish this up, it will be gas. No one has done it for coal so far. And interestingly, when I made this presentation at the Department of Energy a few years ago, when Ernie Moniz was in, we were trying desperately to get oil assays. So the oil assay is a chemical analysis of a crude. And they're done all over the world to sell your crude, but DOE didn't, we thought they'd be a really good either source of assays because we need them for the refining model, or we could get them to do it. And in that meeting, I remember so clearly, they don't do it, and they can't do it because DOE can't, and the Energy Information Administration cannot themselves advance data collection methods. They basically have to let industry give them data, and then they can actually statistically analyze it. But the hurdle to collect new data from industry is very difficult for a Department of Energy, which was very disconcerting for me to hear. But that said, they do a lot of good statistics with the data that they can get, and they slowly eke away at getting new data, like condensate data now that we're fracking everywhere. But in that meeting, someone raised the point, but this is true of coal too. So we know this. I mean, already coal is bituminous, subbituminous, anthracite, lignite. Like, we know there are already types of coal that are quite different from each other. And then you have even coal bed methane, which is a different side of the whole coal industry, whether you put it in gas or coal. So I think that this type of an exercise, I'm speaking with Carnegie Mellon. I think that Carnegie Mellon University is like the area where life cycle assessment was given a birth. And that would be, a real, I think it's very important to continue these. I mean, you could do this for soybeans. You could do this for corn. Like, you could do it for any commodity for that matter. But I do agree that coal would be a very important one to, again, not only know where the emissions lie in the supply chain of coal, but then be much smarter about how do you manage the emissions, as opposed to having the only tool in your toolbox saying, don't use it, which is pretty much the current strategy right now, is just to cut off demand. Yeah.
Anecdotally, there are supply chain models for commodities like palm oil and soybeans.
Yes.
Called TRACE. You look up TRACE, TRACE, global supply and distribution and consumption. On the fire side of things, which is another one of the areas that I work in, it'd be really interesting. I know you guys are interested in contemporary data, and everyone would like to stay up to speed. There's a long record of active fire data from the MODIS sensors that goes back to 2000. So you could see some of these areas of production coming online, which obviously has been a major advance in terms of areas of new gas production and fracking. So you'd see that whole evolution of the gas fields that have come online in the last 20 years.
Yeah.
There's also higher resolution active fire data available from Landsat. And for the conterminous US, they're already produced online and supported by the Forest Service. So if you wanted to take that Eagle, Texas area,
right,
and then disaggregate some of the VIIRS active fire locations and see, is that one big flare or is that a lot of different flares? My understanding is that it might tell you something more about their modes of refining and production. That could be further information.
Yeah.
They're routinely produced for the US. You can get them on the Forest Service website. They're not routinely produced globally, but that's something we can talk about.
Yeah, I think that sounds really interesting. We do have the disaggregate. We're representing these globally, so they're kind of all glommed together. But I know that we have looked at some of those disaggregated flaring data too. And it's interesting because when you look at the Bakken in North Dakota, it's true in Texas, but more true in North Dakota, there are so many different small operators. And some of these operators have access for their gas. They could put it into a pipeline. And some of them don't. And so they're not going to stop oil production. They're just going to vent or flare their gas. And that becomes a really important part of knowing where to look and who to say, we need you to change your practices, or having different rules about that.
Yeah, so MODIS is 1 kilometer, VIIRS is 375 meters, Landsat would be 30-meter resolution.
Right.
So you'd be able to find a lot of those very small flaring activities, the size of sort of individual production wells, in ways that you wouldn't routinely be detecting with the other satellite data.
Yeah. I mean, I didn't mention this, and you reminded me of it, but when somewhere along the line, my colleague at Stanford, Adam Brandt, and I were talking about, we could even use satellite imagery, just not even of of what we're talking about in terms of atmospherics, but in terms of facilities on the ground, where you can start to see what's being added. Like you can actually, a lot of this equipment has a shape, has a pretty knowable shape to it, you know, a tank versus a compressor versus a flare. And you could actually be ahead of what is being planned on the ground, because my hope with the Oil Climate Index right away was not to only make it following as an industry indicator, but to actually help it inform decision-making up front. So as we see what countries are doing, or even places in the US and companies are doing, that you can actually have these conversations about reducing emissions and putting in certain equipment at the outset, or doing certain management practices at the outset, knowing that they're going to be using certain equipment and they're going to be using certain processes. A big one right now is CO2 enhanced oil recovery. Is a huge conversation going on. And the idea there is to take CO2 hopefully out of the atmosphere, although a lot of it's natural, coming out of natural caverns right now, but to take it out of the atmosphere and inject it into the oil field. Okay, you produce more oil, but you're also sequestering, if you're taking, you know, anthropogenic CO2, you're sequestering stuff that was in the atmosphere in the first place. And that's going to be yet new equipment and new managing, and we want to make sure that CO2 doesn't leak. So I think this only gets a little bit more detective, you know, in all of this. And I'm with you. I don't think that it has to be just real time. I mean, I think that real time can get, if you can get it, great, but we've been able to have policy impact with VIIRS satellite data that's not real time data. So it doesn't have to be.
Although I would say that of all the real-time data sets we produce, the active fire data are the most real-time.
Yeah. So we should be.
You can have them within 30 minutes of overpass.
Yeah. I think, and also flares, having worked at Chevron, I know how intermittent flares are.
Yeah.
Flares are, you know, you pass over, and honestly, this is what I heard. I don't know if Chris told me this, Chris Elvidge, but I believe that in the early satellite launch of VIIRS, Russia was horrible. Well, already the World Bank had known Russia was terrible in terms of venting, flaring their gas. And they got much better. And, you know, in the successive years, and it wasn't clear whether they got much better or they figured out when the satellite went overhead.
It's both.
So I think that the idea of, you know, having something that is, you know, real time and watching it and knowing the operations might truth test a little bit more of that as opposed to a snapshot like this.
Okay, nice. So let me define our Japanese satellite first.
Oh, thank you.
You mentioned that it's a 400 hectopascal, but actually you have two instruments on it. The one is looking at the height, and one is sensitive to surface. So you can use the other instrument to get sensitivity to the surface. So you can probably navigate the whole.
Okay.
There's an instrument you can do that.
Okay.
Actually, we're planning to not myself, but my plan is doing that. But if you both the two satellites, you also need this methane at the same time, so you probably could come to I have a question about the methodology. I think you were saying your satellite data is not actually satellite data, but products from CMS product is eligible. That's my understanding. Because the years measure radians.
Yes.
One place it was doing some quantum computing.
Yes.
Estimating the latent heat, they convert that energy into fuel. So I'm not sure how you can separate CO2 emission and methane, especially methane can come out as a leak. So you don't really see a light intensity or anything else.
Does anyone else? Yeah, no, it does. But just back on the VIIRS, yes. As I understand it, because my partner at Stanford, because it was production oriented, the flaring data, he was the one that incorporated that. And as I'm recalling back now from OCI 2.0, we had the flaring data was put out as irradiance, and it had to be converted and recalibrated in order to put it onto this, you know, put it into SCF, you know, standard cubic feet. Like how much gas would that have represented in terms of a volume? Yeah. And on the methane, I don't know well enough how the methane data is collected to answer that, but maybe some of you, it will be a whole different mechanism, obviously, than the heat signature that's coming out of VIIRS.
I think estimating CO2 emission from gas flare, that's the main perspective, objective of the research. And I think he's assuming some kind of laser with this much emission coming out, then dark methane with this much kind of stuff. And so I'm just suspecting maybe use the same data twice or a couple times in your system? Because I don't see how you can divide CO2 emission down to emission. Also, also calculating its estimate to some statistical database estimate.
Right.
So there might be some.
No, let me explain. So we don't use CO2 atmospheric data in any of this.
But what kind of product are you using for that?
From the products we were using the flaring data only, just the flaring data that was coming out of that satellite. The CO2 data you saw represented here in the bars, although flaring is embedded into that from the VIIRS data, it's part of the total, but the CO2 signature from all of the other operations, shear operations, is bottom up. It's basically through a process model that lives on the website that you can go. It's all open source. Actually, and the production model was first supported and developed for the state of California. So it lives in the California Air Resources Board for the low carbon fuel standard. And it's been used for over a decade, this OPG, the Oil Production Estimator Greenhouse Gas Model. So that we're not even verifying, and we're not using any NASA or any satellite CO2 data right now in anything that we've done. I know you're doing a lot of work on that, but we haven't done any of that measurement relationship. And maybe it would be even harder because how would you attribute it right there to that field? So they're separate in my mind. I mean, it's like we have the satellite that has VIIRS that is helping us get this flaring data that we can add in. What we basically have in our model is the flaring to oil ratio. That's all we really had in terms of the mechanism, but we didn't know it. We were using country level data from the World Bank initially to get that flaring to oil ratio. Now we can actually, in the sum of those oil field boundaries, we can get a flaring volume, and that takes the aggregate in that boundary. That becomes our flaring to oil ratio. That becomes part of the calculation in the model to be in the estimate of the total emissions.
So the data this survey created from flaring, that's mainly from an offshore platform, right?
No,
Not inland. The inland?
Yeah, well, you saw the map here that I showed that had the dots. They were everywhere. I don't even know if I noticed that many offshore, but there are offshore. I remember Indonesia has a bunch offshore. Africa has a bunch offshore. I'm thinking of the map. In the US, it's largely onshore and then into the Gulf of Mexico.
Oh, okay.
Yeah,
Okay.
yeah. No, it's global. I mean,
So
it's
plus inland.
They're just static sources.
Static sources.
That's what they're called. So wildfires move and flaring doesn't. So if you see active fire detection in the same place day after day, it's a flare. We pull that out. We want to know that's separate from, say, wildfire detection.
Yeah.
And that is useful for other uses in the static source data.
doesn't it have a different heat signature too? I thought that's what I understood, that flaring and forest fires don't burn at the same temperature.
Yes, that's
Or don't have the same light.
Yeah, you're using combustion temperature.
Yeah.
When you estimate the run cup, you
Yeah.
get the temperature and also the overall.
Yeah.
The estimate. You're using high temperature for both zero and low temperature for run cup.
Yeah.
Right. But at 1 kilometer resolution, they often look the same.
Oh, interesting. So not moving is more important.
So not moving is the real indicator.
Interesting.
Just invariant.
Yeah.
Yeah. Let me make some suggestions that you might find helpful.
Sure.
Particularly if you're interested in prototyping. We're beginning a new series of satellites as part of what's called the SBG, Surface Biology and Geology Program. And I was the original mission scientist for something called Earth Observing 1, EO1, which was the prototype for the Landsat A series. But we have another instrument on called Hyperion. Okay? And we actually, I just pulled it up again, it's been a while, but the headlines and things like the Washington Post was, this gas leak was so massive that NASA saw it from space. The NASA Porter Ranch gas leak was so big it could be seen from Echo Watch. And a whole series of articles, one academic article produced by my colleague, which I'm a minor co-author from JPL, was basically explained the mechanisms and so on. But what happened, high resolution had on one called Hyperion, which ended up basically helping develop the new one that will be going on to this new satellite series we're pushing for. Who builds it's another story because everything's the open competition.
Right.
But we're able to
even have data that's 10 pseudo resolution because we band high resolution. I mean, when the Lancet hasn't pushed that too much, they should. I encourage the guys at OLR. They have a 15-meter band that's, I guess, starting to be used now. But when you look at fires, you can see the structure. You can also derive the temperature, even though we had no thermal band, because in going from, it goes from 0.25 microns out to roughly 0.4 microns to 2.5 microns. I normally think in nanometers, but most people are familiar with microns. But at any rate, you have 160 channels, so to speak, from 1 micron on, and you can do an inversion of that and get the exact temperature. We've used it for looking at lava flows, measuring them, but more importantly, we've looked at forest fires extensively. A colleague here in the engineering division, Dan Mandel, has worked on something called the Intelligent Payload Module, and we were actually bending, we were triggered by the MODIS, which is universal and detect fire, and then we would point in that direction. We could revisit that spot sometimes a day apart because we were a pointable instrument. That's not in the plans for the new one. It will be a survey instrument. But we use it for disaster monitoring. But what's equally helpful is not what we can do for you, but what you can do to influence the way our program runs, because we have a new emphasis on applications. And I've been with the agency for in excess of 50 years now. And so I know that we do need guidance for sure. Now, you have a cohort who's at Carnegie Institution at Stanford. His name is Greg Asner. I don't know if that's a familiar name.
Oh, no, I know Ken and Chris Fields, but I don't know.
Chris Fields is his colleague.
Okay, okay.
And he's a whiz at this. He works with Lancet data, he works with Hyperion data. He also has an instrumented aircraft that can overfly that has a LiDAR on it, has an imaging spectrometer on it, does traditional Lancet bands and a variety of things. I'd encourage you to get in touch with him.
Okay.
And a chap named David Thompson at JPL. I'll give you my card afterwards if you want to. I'll be happy to
That sounds great.
help you out.
That sounds great.
At this point, I'm not actively engaged in research, but I really like to help pass on the lessons learned, particularly the lessons not learned, so they don't repeat my mistakes.
That would be great. We were just looking at Hyperion yesterday. I think it's not coming back to Earth until 2056, even though it was down a long time ago, or a bit ago.
It went down in March.
Oh, it just went down. Is it 20?
Yeah. It was fully functional.
Yeah, and then it will finally, make its way out of orbit.
It was $1.5 million a year, which they thought, we had met our mission a long time ago.
Yeah.
It was viewed as a mission, which it would fail the contest as a mission. Didn't have a clean objective. It really was a facility and there's some regret expressed on the part of some of the leaders now that it's turned off. Just for those of you who look like you're interested in it, the story with Hyperion was we were challenged to turn it off. It took about 3 years worth of funding because it was never built with an on-off switch, in fact. Largely, and so if it kept tumbling around and we even discharged the battery, it would eventually perhaps come back alive. So they had to tamper with the onboard instructions, which normally bring it into safe hold. And what that said, the first instruction was discharge the battery.
Back to square one.
Its orbit was in the process of decaying, but it was potentially a good way of learning about what happens with something, because the complement of instruments and technology was still fully functional.
Yeah, so interesting.
But again, it did require funding.
Yeah.
Great discussion. We have time for one more question. Anyone? Or anyone on the phone line?
Comment.
Yeah.
Somebody else in the room might know better, but some of these products may be obtainable from the data simulation model, GMAO. Not sure. There are some, I think. Integrate all that.
Maybe we may not have the right accuracy to But also we need the satellite data to be assimilate as well.
Right, what I mean is they are assimilating satellite data, producing atmospheric composition from it. So some of it might be useful.
Good. Good, Tom. It's great.
I know, Deborah, you and Fran are not yet onto the gas and methane side of things completely, but there's obviously a major science interest in this room and then in the community on kind of further unraveling the mysteries of the methane budget. So there are
Yes.
efforts here with Schemati data and also with Tropomi data, but there also is a global methane budget effort by the Global Carbon Project. And we've got colleagues here, Ben Poulter, who's not in the room today and maybe online, has been heavily involved with that. And so essentially bringing together whatever we're gaining from the bottom-up side with what we have from
Yes.
the top-down side and the natural source information seems really valuable. I see that as a positive way forward, even if there's not time for it today.
I think that sounds great, because I have to say that now that we're struggling to model gas as we did oil, it harkened me back to my days at Shell. Early on, I was told, I was given a budget to say, go onto the field, this is 1982, go and produce a fugitive emission protocol for us. But don't measure methane, actually. That was a little thing, because it wasn't an air pollutant contributor. It was only C2+, but whatever. Go measure your fugitive emissions. And it was the only thing I ever failed at there. I felt like that now I realize gas is hard. And that's not even the only methane source out there. Like, you know, methane is hard. And I think it's going to take a lot of these bright minds to make a lot of good sense out of it, how to manage it. And it's the right thing to do. So I will talk, you know, to colleagues about that in any way I can help and contribute.
Thank you.
That'd be great.
And I think it's a perfect segue. The next seminar in October, we're going to have Stephen Hamburg.
Oh.
He's the chief scientist
On the
EDF,
methane satellite.
and he's going to be coming to talk about methane sat and monitoring methane using satellites. So
Good.
that's
Good segue.
There is a lot of interest here
This is
in
great.
methane. So
Well, I'm just thrilled that you're all here. I mean, not sitting here today, interested in all of these issues. I think it's fantastic.
yeah. So thank you, Deborah.
Thank you.